Hello students, myself Amrita Roy. Today we are going to study a part of the unit filter circuits of the subject network analysis. Let us go through the contents what we are going to study about today. We are going to study about network synthesis, that is the concepts of pose and zeros and the definition and relationship between Napier and decibel. Next, network synthesis. So, what is the concept of pose and zeros? Before starting, we need to know what do we mean by a transfer function. A transfer function is basically the Laplace transform of impulse response of output to the Laplace transform of impulse response of input with all initial conditions as 0. So, it provides a basis for determining important system response characteristics without solving the complete differential equation. As defined, the transfer function is a rational function in the complex variable S equals to sigma plus j omega. That is, in case of Z transform, we will represent transfer function as Hz equals to Pz by Qz. So, if we write the equation, we will get B naught plus B1 Z inverse plus B2 Z to the power minus 2 and so on. And in the denominator, we will write as 1 plus A1 Z inverse plus A2Z to the power minus 2 and so on. So it is often convenient to factor the polynomials in the numerator and denominator and to write the transfer function in terms of those factors. So if we convert the transfer function into frequency domain, we will represent it as Hs equals to Ns by ds, which will give us k multiplied by s minus z1 multiplied by s minus z2 and so on. And in the denominator, it will give us s minus p1, s minus p2 and so on. And k is the constant here. K is the system gain. And from this equation, we will learn how to calculate the pose and zeros of a transfer function. So in the numerator, we can see we have s minus z1, s minus z2 and so on. So what is basically the zeros of a transfer function? The zeros of a transfer function are basically the frequencies for which the value of numerator of transfer function becomes 0. That is, suppose we are taking the first one, that is s minus z1. So, if we substitute s by z1, then the whole numerator will become 0 as z1 will get cancelled. So, for calculating the zeros of a transfer function, we will substitute s minus z1 equals to 0 for that equation. Now, for calculating the pose of a transfer function, we can calculate the pose of a transfer function by substituting the denominator, that is s minus p1 equals to 0. That is, if we substitute s minus p1 equals to 0, that is, we will get s equals to p1. So if we put the value of s as p1 in the equation below, that is in the denominator, the whole denominator becomes 0. So the pose of a transfer function are the frequencies for which the value of the denominator of the transfer function becomes 0. So pose and zeros are present in the denominator and numerator respectively for a transfer function. And calculating pose and zeros of a transfer function are important, specifically pose, because they determine the stability of the system. So we will concentrate mainly how to calculate the poles and zeros of complicated equations. So all the coefficients of polynomials of ns and ds are real. Therefore, the poles and zeros must be either purely real or appear in complex conjugate pairs. In general, for the poles, either p equals to sigma or else p plus 1 equals to sigma plus j omega. The existence of a single complex pole without a corresponding conjugate pole would generate complex coefficients in the polynomial. Similarly, the system zeros are either real or appear in conjugate pairs. So what do we mean by that? In this equation, in this graph, you can see we can form an equation by looking at the location of poles and zeros. So in this figure, we can see that there are some cross marks and some zero marks. So first, before writing down the transfer function, by observing the location of poles and zeros in a graph, we need to see the values of poles and zeros and where they are located. So we can see on the right hand side of the graph and on the left hand side of the graph. On the right hand side of the graph, there are no cross or zero symbols present. The x-axis, that is the sigma axis, is basically representing the real axis, and the y-axis is representing the imaginary axis. Now on the right half of S-plane, we will consider this the graph as the S-plane for plotting poles and zeros. So on the right half of S-plane, there are no poles or zeros present. But on the left half of S-plane, there are, we can see some cross marks and zero marks. The cross marks are basically representing the pole and the zero as zero. I have identified them on the left hand side of the graph, that is on the upper part. You can see that cross is denoting pole and zero is denoting zero. Now we can see the value of cross mark on the real axis as -1. That is, one pole is located on the real axis as -1, and the value of 0 is also located on the real axis as -2. So on the real axis, we are getting one pole as -1 and one 0 as -2. Now if we look on the second and third quadrant of the S-plane, we can see that on the second quadrant we are getting a pole that is a complex conjugate pair. That is, the value of the poles are the same, but they are present one in the positive part and one in the negative part. That is, the complex conjugate part is basically one is carrying a positive value and another is carrying a negative value. That is, if we write the equation, or if we want to find out the pole of this complex conjugate, we will represent it as sigma plus j omega format. So for writing it in sigma plus j omega format for this pole, the real part will be written for the sigma value, that is sigma is here -1, and for the j omega value we will see that it is coinciding with j2 on the second quadrant. So for omega we will write as 2. So the complex conjugate value of the poles will be, one will be -1 plus j2, another will be -1 minus j2. So for calculating the complex conjugate, we need to look at the real part of the pole and also on the imaginary part of the pole. So the location of one pole is on -1 plus j2 and another location is -1 minus j2. So if we write the transfer function of this S-plane, we will see that the numerator, that is the location of zeros. So location of zeros, we see that on the S-plane we have only one 0 present. So the numerator will be written as S plus 2 and the denominator, that is the location of poles, will be represented as there are 3 poles present, one on the real axis and 2 poles on the second and third quadrants, that is complex conjugate pairs. So the denominator will be represented as s plus 1 and the complex conjugate pairs will be represented as s plus 1 minus j2, s plus 1 plus j2. So the whole transfer function can be written as s plus 2 divided by s plus 1 into s plus 1 plus j2 and s plus 1 minus j2. So this is the complete transfer function if we want to plot it from the S-plane graph. So it's very easy to calculate. Next is the pole zero plot. A system is characterized by its poles and zeros in the sense that they allow reconstruction of the input and output differential equation. So in general, the poles and zeros of a transfer function may be complex and the system dynamics may be represented graphically by plotting their locations on the complex S-plane, whose axes represent the real and imaginary parts of the complex variable S. Such plots are known as the pole zero plots. It is usual to mark a zero location by a circle and a pole location by a cross. So the location of poles and zeros provide qualitative insights into the response characteristics of a system. So we have seen in the previous example how to plot poles and zeros. Similarly, I have provided here an example where I have provided a transfer function as y equals to 5, which is the system gain, multiplied by s square plus 2s plus 1 divided by s square plus 2s square plus 2s plus 40. So if we do the quadratic equation of the numerator and denominator, we can see the numerator is having s plus 1 into s plus 1 divided by the denominator is having s plus 4 into s square minus 2s plus 10. So we can see that if we break s square minus 2s plus 10, it will give us a complex value. Now from the above example, it is seen that it is not positive real because it has 2 poles in the right half of the S-plane. If you calculate, you will get the value of poles on the right half of S-plane. So if any pole is present on the right half of S-plane, it is representing that the system will be unstable, because the stability of the system depends on the location of poles on the left half of S-plane. So whenever we can see that after calculating the values of a pole from a transfer function, if it is found that the value is coming out to be positive and it is on the right half of the S-plane, that means the system is completely unstable. Similarly, in the next equation, in the next function, you can see we are getting the equation as s into s square plus 5 and s square plus 1 whole square. So which is not positive real because of multiple poles on the imaginary axis. So I have provided here a few graphs of the response if poles are located on the left half, on the right half, on the how to get the marginal stability. So if poles are located on the left half of S-plane, we will get overdamped response. If poles are located on the imaginary axis, we will get undamped response. If poles are complex conjugate, we will get underdamped response, and if the poles are located on the left hand side and they superimpose each other, we will get critically damped response. Next is the definition and relationship between Napier and decibel. Napier is basically a unit of measurement used in comparing voltages, currents and power levels, especially in communication circuits. So the difference between two values in Napier's is equal to the natural logarithm of their ratios for voltages and currents, or to half of this for power differences. And the decibel is basically a unit of measurement used to express the ratio of one value of a power or field quality to another on a logarithmic scale. The logarithmic quantity being called the power level or field level respectively. It can be used to express a change in value or an absolute value. The relationship between nipper and decibel is basically given as 1 nipper NP is equals to 20 by log 10. That is, it is giving us a value of 8.685889638 decibel. So this is the basic relationship between nipper and decibel. And if definition comes, just write the full definition of nipper and decibel and write down the relationship between them. Thank you. In the next presentation, that is in part 2 of filter circuits, we are going to study about the passive filters, active filters, their advantages and their applications.